Okay, so moving on to problem 14, which deals with elasticity. And we know from the relation of Young's modulus to the stretch that the strain is given by the Young's modulus times the length change over the original length. And that gives us a relationship for the change in length, which is equal to the force times the length over the area times the Young's modulus. And since we have a composite, then we have to do a superposition and say that the overall change in length is going to be the change in length for the steel part plus the change in length for the aluminum part. And that means that we have the force on the wire times the length part that is made of steel divided by the area of that wire times the Young's modulus for steel, and similarly for the aluminum part. And now if we apply all of these given values, we can find first that we have a common part of F over A, and this gives us length of steel over Young's modulus of steel plus aluminum length divided by Young's modulus for aluminum. And the force that's acting on this is nothing more than the weight of the 5 kilogram mass. So to get the weight, we would multiply by G. The area depends on pi r squared, and in this case the radius is 0.5 times 10 to the minus third meters, quantity squared. And now the steel part is 1.5 meters. The steel's Young's modulus is 2 times 10 to the 11th Newton per meter squared. And similarly, the aluminum part is 1.5 meters, but its Young's modulus is 0.7 10 to the 11th newtons per meter squared. So if we do this, we get a change in length of 1.81 times 10 to the negative 3 meters, which is the same as 1.81 millimeters.